Hello, everyone. Welcome to this second lecture in this practical introduction to quantum computing. And I would like to start saying thank you to you all. We had a very good reception to the very first lecture in the course last week. We had more than 1,500 people watching the live webcast and many thousand people watching the recording. We received a lot of positive feedback, so we are really very happy with the reception, and we thank you for all your interest and all your feedback. We also received a lot of questions, and as I told you in the first lecture, I will try to address the most popular ones in the beginning of the lecture. So by far, the most popular question last week was, when will the recording be available? Okay, so well, now you know that the recording is available. It will be surely the recording for this second session again available on Monday. And you can find the links on the Indico page for the lecture. You will see that there is a link to a recording on the CERN document server, the CDS, and we also have provided a recording on YouTube. Okay, so you can use whatever it's better for you. Some people were experiencing some problems watching the CDS version, so now you can also watch it on YouTube. And also in YouTube, you have the opportunity of turning on the subtitles, which are automatically generated. I don't know if my accent is good enough for the algorithms of YouTube to catch everything that I say, but well, at least you can turn those subtitles on and probably understand a little bit more of what I'm saying if you have trouble with my accent. So again, on Monday you will have the opportunity to access the recordings. Check the web page, the Indico page for the second lecture, and be careful not to click on the webcast. The webcast is only available live, but there will be links to the CDS and the YouTube recordings. So that's the most popular question. The second one was about the possibility of having a list of textbooks or resources that you can check in order to learn more about what we are explaining in the lectures, or to go farther in your study of different topics in quantum computing. So I have compiled a list, and I have uploaded this file to both the Indico page for the first lecture and for the second lecture. And there you can find a series of books and online lectures, lecture notes that I think are interesting or are useful in order to learn more about quantum computing. In particular, the first one is a book that is titled Quantum Computing for Computer Scientists by Janowski and Manucci. And this is a very clear introduction to quantum computing. In fact, it starts completely from scratch. From the definition of what complex numbers are, of what Hilbert spaces are. So even if you don't know much about the algebra or the mathematics behind quantum mechanics, you can start there. And I think you will get a clear view of the tools and the mathematical concepts that you need. And then it goes on explaining more about, of course, qubits and quantum gates and some algorithms. So I think that is a good start, and I have also provided other resources, other books, other lecture notes and courses that you can check in order to learn more. I will give you pointers at certain moments in the lecture to which of these resources you can check in order to learn more about a particular topic. And we also had a lot of questions about the possibility of interacting more during the live session. You know that we have this Zoom call with some people which are invited to participate, and they can, of course, interrupt me at any moment and ask me questions, but this is difficult to provide this opportunity to all the people that are watching, more than 1,000 people. So we are working on different possibilities in order to give you more interactivity. I have been trying to answer all the emails with questions that I have received, but in the next few weeks, we hope to have some other tools by which you can interact live during the session. And let me remind you to the attendees on the Zoom call that please feel free to interrupt, to raise your hand with the option in the Zoom application, or to write in the chat. I will be trying to check the chat and the list of participants to see if there is any question. Also, there were some questions about the possibility of installing all the frameworks and all the libraries that you need in order to run Qiskit locally. And I have uploaded a link to both the Indico page for the first lecture and the second lecture, with a website in which you can see all the steps that you need to perform in order to install Qiskit locally and run the code that we are showing here in the lectures on your own computer. Of course, if you use the IBM Quantum Experience, you don't need to install anything. You just need to sign up and log into the cloud framework, and then you can upload your code and run it there, or create your code there. But if you want to run it locally, you can also do that, and you only need to follow the instructions in this link. So I think that is more or less all the questions, or the most popular questions that we have received. So I invite you again to check the information on the web page, the Indico page. You have the slides, you have this list of resources, you have these links with the installation procedure, and some links to the tools that we are using. Okay, so without further ado, let me go to the content of today's lecture, and let me start by let me show you the slides. Let me start by recalling the different. I'm going to go out from this. Okay, sorry, I have lost the chat box and the list of participants. Okay, now I'm done. Okay, so sorry for this problem. I'm going to start by recalling the quantum gates that we have already studied. Okay, remember that quantum gates are the way in which we can transform the values of the states of the qubits and then perform different operations on them. And we had studied the X or NOT gate, which just changes 0 into 1 and 1 into 0. We have also studied the set gate, which leaves 0 unchanged and introduces a phase of -1 in front of 1. Okay, and of course, all these gates act linearly, so they can be extended to general qubits in superposition, but we only need to state their action on the basis. Okay. We also had introduced the Hadamard gate, which is a very important gate because it allows us to go from one of the basic states, 0 or 1, into a state which is in superposition. And these are very important states that we have given a name to. We are calling plus the state 0 plus 1 over square root of 2, and minus the state 0 minus 1 over the square root of 2. Okay, so these are the gates that we had already studied, and with this we were able to construct a very simple circuit which allowed us to generate random bits. Okay, and this is what we did last week. Of course, we have more quantum gates. We have X, we have Z. it is natural to think that we also have a Y gate. And in fact, we have a Y gate, which is not so commonly used, because you can obtain something that is equivalent to this Y gate just with X and Z. But the X, Y, Z gates, together with the identity, are very important because they constitute what we call the poly gates. And for the physicist, an alternative notion that is very popular in physics is this notation here: sigma X, sigma Y, sigma Z. And we will be using these poly gates a lot. And for instance, when we talk about quantum error correction, we will see that these gates form a basis of the different errors that we can have in a given qubit, and then we will study the composition of a general error gate into these different gates. Okay, we also have these S gate and T gates, which are similar to the Z gate. You see that they are diagonal gates, and they leave the zero state unchanged, and they introduce a phase in the one state. Okay, so this is a particular case of something that we are going to study in a few slides, which are called rotations of the states of the qubits. Okay, and they will be very important also when we move on to 2-qubit states, because we will be doing controlled rotations in several different algorithms. Okay, so these are other important gates. But in order to introduce the most general gates that you can perform on quantum, on one single quantum bit, we need to study a very, very interesting and very beautiful representation of the state of a qubit. And this is what is called the block sphere. So what we are going to do is to represent the state of a qubit on the surface of a three-dimensional sphere. And for that, of course, we need two parameters, because we can parameterize the different values on the surface of a sphere with just two values. Okay, and this may seem a little bit difficult at the beginning, because to give the state of a qubit, we need two complex numbers, and each complex number is of course formed by two real numbers. Okay, we can write any complex number as a plus the imaginary unit I times b. Okay, so it would seem that we would need 4 different parameters to represent the state of a qubit. But of course, one of them is not free, is dependent on the others because of this normalization property that we have. We know that the squared absolute value of the amplitudes of the state need to up to 1. So this removes one of the degrees of freedom that we have. In order to remove another degree of freedom, and then to have just 2 numbers that we can use to represent the state on the surface of a sphere, we are going to notice that, of course, any of these 2 amplitudes, alpha and beta, can be written as a phase times the magnitude of the complex number. Okay, and of course, because these magnitudes, these absolute values of the complex numbers need to up to 1 when squared, we can represent them as the cosine and sine of a certain angle. Okay, here I have chosen to represent these cosines and this cosine and sine as the cosine and sine of half an angle of half theta, for reasons that will become apparent soon. Okay, but of course I can choose theta such that the magnitude of these 2 numbers are given by the cosine and sine of half this angle. Okay, and then we have these phases in front of the magnitudes. Of course, these are complex numbers whose absolute value is 1. And in fact, if you think about what you can do with a qubit, you will see that these phases that are in front of a whole state are not physically important. What we can do with a qubit is either transform it with a quantum gate, and this is linear operation, and then all the phases that are multiplying the whole state will go out by linearity, okay? So the transformation will not see the global phase that is affecting the whole state. And also when we measure the qubit, we take the square root of the square of the absolute value of the magnitude. So any global phase that is multiplying the whole state will not affect the probabilities of measuring one result or another, okay? So in any case, either if I'm transforming my qubit with a quantum gate or if I'm measuring the state, a global phase that affects the whole state is not important. I cannot, in fact, determine that, that global phase with any physical experiment, okay? So what we can do here is to multiply these two numbers, alpha and beta, with a global phase. And we are going to use that global phase to eliminate, for instance, this phase here in alpha. So finally, we can write the general state of a qubit in this compact form in which we only depend on theta and on this angle phi, okay? So we have reduced the four numbers that in principle we thought we needed for the determination of the state of qubit to just two. And these two numbers, these two angles, can be used then to represent the state of the qubit in the Bloch sphere, in a sphere, in a unit sphere in 3 dimensions, where the angle theta is, so to say, the latitude of the qubit, and the angle phi is the longitude of the qubit. Okay, so here you see that we have this angle theta, which measures the displacement of the qubit with respect to the North Pole. Okay, we are situating the North Pole, the zero state in the North Pole, and we are situating the one state in the South Pole. And this is the reason why I chose this angle to be half theta and not theta, because the range of values that we need for this cosine are between 0 and pi over 2, and we want to have here pi, an amplitude of pi radians, okay, between the North Pole and the South Pole, okay? And when we divide this by 2, we obtain the correct range for the values in the Ket expression of the qubit, okay? And then phi is the longitude of this qubit in the sphere, which states or represents the displacement with respect to the x axis in the sphere. Okay, so we will have 0 on the North Pole, 1 on the South Pole, and for instance, all the values that are on the equator will have exactly the same magnitude for the amplitude of 0 and the amplitude of 1. And then when we measure any of the values in this equator, we will have 0.5 probability of obtaining 0 or of obtaining 1. Okay, in fact, you can see that the closer the state is to the North Pole, the higher the probability that we have of obtaining 0 when we measure, and the closer the state is to the South Pole, the higher the probability we will have of measuring 1 from this state. Okay, so with this representation in mind, that to physicists probably is already very well known, because this is also the way in which you can represent the spin of a half spin particle. With this representation in mind, now we can define a new family of transformations of quantum gates that we are going to be using a lot, okay? And these are what we call the rotation gates. These are the transformations that we can think of doing in the Bloch sphere, in which we fix an axis and then we turn the sphere around that axis a certain angle, okay? And we can do this to start with for the axis X, Y, and Z. The axis Z, of course, is the vertical axis here. The axis X is this axis that is perpendicular to the screen, that is coming up to you. And this is the axis Y is this horizontal axis in the sphere, okay? So we can think of actions in this sphere, quantum gates, unitary transformations that just fix one of these axes and rotate the sphere around this axis. And mathematical expressions for these rotations are given here in this slide. We can construct them as the exponential of either the X, Y, or Z gates that we already know, with the minus the imaginary unit, and again half an angle in order to have this range of in this case of P or 2P angle in the Bloch sphere, okay? And if you expand this expression for the exponential of these different gates, you will notice that since X squared, Y squared, and Z squared are all equal to the identity, when you give the power series for this exponential, you will have alternative identity matrices and X, identity and X, and so on, or identity and Y, or identity and Z, and the coefficients that go in front of the identity and the X, Y, and Z matrices in this expansion are exactly the power series for the cosine and the sine, okay, with this factor, this phase of minus Y in front of the sine. And if you replace here the values of the identity matrix and the X, Y, and Z matrices, you obtain the expressions for the rotations, okay? It's not very important to learn or to understand completely all these derivations. For instance, you can check more details on in the book by Nielsen Chuang and Michael Nielsen and Isaac Chuang, which I have included in the recommended books. But it's not that important. What is important is to understand that this is a rotation of the Bloch sphere and that this is a transformation that we can do with the qubits, okay? It is also interesting to notice that, as we have mentioned, a global phase is not important, it's physically irrelevant, okay? So for instance, here in this expression for the rotation around the Z axis, we see that we have I to the minus e to the minus I theta over 2, e to the I theta over 2 on the diagonal of the expression of the matrix. We can multiply this matrix by a global phase. In this case, for instance, I can multiply by e to the I theta over 2 to remove here this complex number and to obtain 1. And then, of course, here I will obtain e to the I theta, okay? And then when I substitute the value theta, for instance, for pi, I obtain exactly the expression of a matrix that we already know, which is Z, okay? So Z, in fact, is a rotation of pi in the Bloch sphere around the Z axis up to a global phase, okay? And the same happens with X and Y, and also with the matrices for S and T that we had defined earlier. All these are rotations around the X, Y, or Z axis, depending on the expression of the matrix. In fact, this is a more general situation. And when you have a unitary matrix acting on one qubit, when you have a quantum gate acting on one qubit, in general, you can always, oh, sorry, somebody is telling me that there is a problem with the slides. I will try to remove them and upload the new ones. Okay, okay. So I will have a break, a 5 minutes break, and I'll try to change that. Okay, sorry about that. Okay, so I was saying that in general, when you have a quantum gate acting on a qubit, you can always find an axis such that this quantum gate is a rotation around that axis in the Bloch sphere. I won't give you the details. You can check them in the book by Nielsen and Chuang, for instance. But this is something that it's interesting because then we can see all the transformations that we are doing in them with the qubits as just rotations in this Bloch sphere, and this will give us an intuition of what is happening. Okay. Also, an expression that is sometimes useful is this decomposition that I have here at the bottom of the slide, in which we give any possible one qubit quantum gate as the composition of a rotation around the Z axis, then a rotation around the Y axis, and then again a rotation around the Z axis. My three-dimensional intuition is very bad, but maybe you can see this, that any rotation around an axis on the sphere can be decomposed in these three rotations. If not, this is something that you can just check algebraically, and there are details, for instance, in the books that I have been mentioning. Okay, but this is an expression that I will be using on later when we talk about control gates. Okay, so this is something that we are going to use. Finally, to conclude our description of what we can do with one qubit, the different possibilities of transformations, the different ways of representing the state, measuring, and all that, it is important to notice that, of course, we are in a Hilbert space, so we have an inner product, okay? And remember that we are representing each quantum bit as a column vector. When we want to perform the inner product, what we can do is to, of course, transform the first column vector into a row vector, and also we need to take the conjugate of the amplitudes because we are in a complex space, and the inner product is taken with the conjugate of the values of the first vector. And then we obtain this expression, which is the normal expression for the inner product. But there is a simpler way sometimes to compute this inner product that we will be using a lot by using this Dirac notation, of which we have introduced already a half, which is the Ket notation. We have said that this zero in these strange brackets is something that is a column vector. And the same goes for this y for this one here. Okay, so when we want to have a row vector, what we do is to write what we call a bra, and the bra is this angle in the opposite direction that we have here for this expression. And then when we have, for instance, this bracket with 0 and 0, we are computing the inner product of the two vectors. Okay, so we are doing this with the expression for the vector 0, and we are computing this inner product in a more compact form. And it's easy, of course, to check that the inner product of 0 with itself and 1 with itself is 1. You only need to substitute here the values. Remember that 0 is the vector column 1, 0, and 1 is the vector column 0, 1. And of course, also these vectors are orthogonal. So the inner product 0, 1 or 1, 0 is 0. And again, you can check that. But this is something that you can use in general only these expressions here to compute the inner product of any two qubit states in a more simplified way. You write the bra for the first state, which is this one here. You write the ket for the second state, and then you distribute the operations, and you check that you only need to compute the inner products of the basis states, and then you recover exactly the same expression here. This might seem more complicated in this situation because we only have two coefficients for each vector, but in general it's very, very useful, and it's one of the most interesting properties of this bracket notation, this Dirac notation. Okay, and finally, something that I want to mention is that we are dealing with orthogonal bases. We are dealing with orthogonal states whose inner product is 0, and you would expect these vectors to have to form an angle of p/2 of 90 degrees, and this is true if we represent them as usual vectors in the plane. But since we are representing them on the Bloch sphere, and remember that we are stretching the angle from pi/2 to pi, what we will have is that orthogonal states are on antipodal points in the sphere. They are in opposite poles of the sphere. So here, for instance, 0 and 1 are in opposite poles of the sphere, and they are orthogonal. Okay, so this is something that it's important also to notice, that the points that are orthogonal in the Bloch sphere are those that are exactly opposite. Okay, I want to show you all this information in a more graphical and more hands-on way. So I'm going to go to the Quirk simulator that I showed you the last time. Okay, I think you can see my screen now with the Quirk simulator, and I will show you the effect of these transformations, the effect of a global phase, the effect of a local phase, and this idea of the points that are opposite in the sphere being orthogonal. Okay, so I will first start by applying just the X gate to the zero state, and you see here that when I don't have the X, I have the 0 vector, which is on the north pole of the sphere. When I apply the X, now we have the 1 vector, which is on the south pole. Okay, now I'm going to apply the Z gate, which you may remember that introduces a phase of -1 in front of the 1 ket. Okay, so if I put here a way of visualizing the amplitude of this new vector, you see that is the magnitude on the ket 1 on the basis state 1 is 1, but with a minus, and this is reflected here in this direction of the phase that you see in this sphere. Okay, if I remove the Z, notice that the phase is pointing in the X and the positive X direction, and if I introduce here the Z, then we have the phase in the other direction. Okay, and then you may wonder, well, this is a global phase because it's affecting the whole state. It's a -1 in front of the 1. This is not important. Okay, yes, in this case this is not important, but notice what happens if I apply this Z gate after I apply the H gate. When I apply the H gate, well, notice first that I obtain a point, which is the plus state, which is, of course, on the equator of the Bloch sphere. And the amplitudes for both 0 and 1 are 1 over square root of 2, okay, with a phase of 0 degrees. Now I'm going to do the same, but applying also the Z gate. And I'm going to show you here the amplitudes in this case. In this case, the amplitude for this state is going to be negative in the case of 1. And notice that this has made the state change to an orthogonal state. Here we have the plus state, and here we have the minus state. This is 1 over square root of 2, 0 minus 1 over square root of 2, 1. Okay, and this is orthogonal. They are points that are opposite in the Bloch sphere. So the moral of this is that, well, the set gate introduces a phase, and when this is a global phase, for instance, when we apply it to 0 or to 1, just to the basis states, then this is not important. But when we applied it to a superposition state, then we have a relative phase. The phase is only on the part of the amplitude that affects the 1, okay? And this can lead to very different states. In fact, in this case, we have states which are completely orthogonal, okay? And the last thing that I wanted to show you with the Quirk simulator is how the rotations act, okay? So here we have a very nice way of representing rotations on the Bloch sphere. This z to the power t, y to the power t, x to the power t are equivalent to the rotations that we have defined. So for instance, if I add here this rotation, which is a counterclockwise rotation around the y axis, you see that here in the Bloch sphere, we are obtaining a state that is, of course, rotating around this axis, okay? I'm going to create here the state 1, and I'm going to rotate it exactly with the same rotation. And you see that we obtain always points that are rotating around this axis, and they are always orthogonal, okay? Because if I start with orthogonal states, the 0, which is in the North Pole, the 1 that is in the South Pole, and then I rotate around one axis, of course, the points are going to be always opposite, and they are going to remain orthogonal. This is to be expected because unitary transformations keep the inner product, keep the angle between the states, okay? But this is a nice way of watching this in action. And for instance, if I do the same with the X rotation, we will have the same effect, but now we are rotating around the X axis, okay? If I do the same with the Z rotation, you will notice that in this case, the states do not change. They remain on the North and South Pole because the Z rotation, remember that only introduces a global phase to the 0 and the 1, okay? And in this case, this is not physically observable, and in the Bloch sphere, it does not change the state, okay? So I think this is a nice way of understanding the way in which one-qubit quantum gates act. I don't know if there is any question about this. Okay, is it clear? Everything is clear? Okay, so let me go back to the slides. And we had already talked about this simple quantum circuit that it's able to generate random bits. But now we are going to see the first application of all these concepts about qubits, measurements, quantum gates that we have been studying in a practical situation, okay? We are going to study what is called the BB884 protocol, which is a protocol that can be used to encrypt data or to facilitate the possibility of encrypting data. Okay, so let's imagine that we have two people, Alice and Bob. This is a common way of naming the participants in a cryptographic protocol. Alice for A, has nothing to do with the Alice at CERN as far as I know. And then Bob for B. And this Alice and Bob want to communicate secretly, okay? Alice wants to send Bob a message that we are going to call M. We can consider that this message is, for instance, a binary string. But there is a problem. They are communicating over a channel that is not secure. So there might be someone there, which we usually call Eve, which is eavesdropping, is trying to learn something from the information that Alice is sending to Bob, okay? So this is a problem that was already solved in the middle of the 20th century with a seminal work by Claude Shannon by a protocol which is called the one-time path. So what we need to do in order to facilitate the secure communication between Alice and Bob without anyone that is listening to the channel learning anything about the message is to encrypt this message by computing the XOR with another string K, which is what we call the key, which is as long as the message. Okay, so this is a random key, a random sequence of zeros and ones, which Alice and Bob know, but the other people, Eve in particular, do not know. So this is a secret key. Okay, this is also what we call secret key cryptography. Okay, and it is easy to show that if this key is as long as the message and is never reused and it's generated completely at random, then it is impossible for anyone to learn anything about any information about the message M. Okay, but of course Bob can recover this message because he can compute the XOR of the message, the encrypted message X that Alice sent to Bob with the key that he knows, okay? And then since we are computing the XOR of the same string twice, the 0 with the 0 gives 0, the 1 with the 1 gives 1, and Bob is able to recover the original message. Okay, so this is a very well-known protocol that is unconditionally secure, and this is something that we can use over an insecure channel to give perfect secrecy to two parties that want to communicate. Of course, the problem is, you may have noticed that we need a key that is as long as the message, okay? And we cannot reduce this key, okay? So this is a problem because then if Alice and Bob are not together or have not been together in the past, if they have been together, they could have used that opportunity to exchange some keys and to set the values of these keys for future communication. But if they are apart or if they didn't meet in the past ever, this is difficult. This is difficult because then they have to share this secret key, and it has to be as long as the message. So if they have a secure channel to communicate this key, they can directly communicate the message. Okay, so this is a problem. For this situation, which is what we call the problem of key distribution, several different protocols have been proposed, okay? Classical protocols. For instance, there is this famous Diffie-Hellman protocol. I won't go into the details. You have here an image explaining how this goes, and this is a very famous protocol which can be used for key exchange, for key distribution. Of course, you can also use, instead of secret key cryptography, you can use public key cryptography, like, for instance, the famous RSA protocol, okay? But these protocols all have a problem. And the problem is that they are not unconditionally secure. The one-time path is unconditionally secure, provided that the key is completely secret, is completely random, is not reduced, is as long as the message. But in these cases, we are in the Diffie-Hellman protocol or in the RSA protocol, we are relying on what we call hardness assumptions. This is the assumption that several algebraic and number theory problems are difficult to solve with classical computers, okay? And then, for instance, for the case of Diffie-Hellman, we rely on the fact that computing what is called the discrete logarithm is difficult. It takes a lot of time. And in the case of RSA, we rely on the fact that we think that computing the factors of a big integer number, it's also very hard for classical computers, okay? But the problem is that quantum computers can break both protocols, can solve these two problems, the discrete logarithm and the factorization problem, in an efficient way, okay? So here we have a problem. We cannot use this kind of key distribution anymore. Fortunately, in 1984, Charles Bennett and Gilles Brassard, this is why we call this protocol the BB84 protocol, B from Bennett, B from Brassard, and 84, the year in which it was proposed, to perform this quantum key distribution to allow Alice to send a key completely in a complete secure way to Bob by using properties of quantum information processing, by using properties of quantum physics, okay? So let's see how this works. This is it's quite a simple idea, but it's very, very beautiful. And it will show how this possibility of using different bases to encode the information, what we call conjugate coding, this possibility of using superposition is very useful for different information processing tasks, including this quantum key distribution, okay? So what Alice is going to do is first generate the key, okay? She wants to send a key to Bob, so she generates a string of random bits. Of course, we know that she could do this, for instance, with a quantum computer. I'm writing here that she can do it with the H gate plus measure. I mean, this is, in practice, she should do some post-processing on these bits, but let's imagine that she has a perfect quantum computer and she can produce these random bits. If not, there are other protocols. I will tell something about this at the end of this lecture, but she first generates this string of random bits, okay? Then, for each bit on this string, she chooses randomly again whether she's going to encode it in the 0-1 basis or in the plus-minus basis. Remember that these bases are orthogonal bases of the Hilbert space of 1 qubit states, and we have the 0 on the north pole of the Bloch sphere, the 1 on the south pole of the North sphere, and the plus on the equator closer to us, and the minus on the other part of the equator. Okay, so these are two bases which are orthogonal because they are in opposite poles of the sphere, but they are not orthogonal between themselves. I mean, plus and 0 are not orthogonal, plus and 1 are not orthogonal, minus and 0, minus and 1 are not orthogonal. And this is going to be important, okay? How can she decide, or how can she encode the information in either the 0-1 or the plus-minus basis? Well, she can decide to use the H gate or the X gate accordingly. For instance, if she wants to create the state 1, she applies to the initial state, which is always 0, the X gate. If she wants to create the plus state, she applies the H. If she wants to create the minus state, she can first use the X gate and then the H gate. Okay, we already know how to do this. Okay, so she can create all these states. And then we suppose that there is a quantum communication channel between Alice and Bob that needs not to be secure. Okay, maybe Eve is able to tap into this channel and try to see what is going on with the information that Alice is sending to Bob. And we will deal with this situation later. But for now, Alice can send these qubits to Bob, okay? And then Bob, each time that he receives a qubit, he also randomly and independently of Alice decides whether to measure this qubit in the 0-1 basis or in the plus-minus basis. What do I mean by measuring in these two bases? Well, measuring in the 0-1 basis is what we already know by measuring. We measure, and the amplitude of 0 will give, when squared, will give the probability of obtaining 0. The amplitude of 1 will give, when squared, the probability of measuring 1. And to measure on the plus-minus basis, we first rotate the sphere. We apply this H gate that is going to move the plus state to the North Pole and the minus state to the South Pole. And then we measure, okay? And this gives us exactly the same result as if we computed the amplitude of the state with respect to plus and minus, okay? So what we do is what Bob does is, when he receives a qubit from Alice, he decides whether to apply H or not, and then he measures, okay? And depending on the result that he obtained, he writes down a bit for the possible key that he is going to share with Alice. So if he measures in the basis 0-1 and he obtains 0, he writes 0. If he obtains 1, he writes 1. If he measures in the plus-minus basis, if he gets plus, he writes 0, and if he gets minus, he writes 1. Okay? So now, these are the first two phases of the protocol. The first is Alice sending these qubits. The second one is, or in parallel, Bob measuring these qubits. So now they have both two sequences of bits. Alice has the sequence of bits that she has generated in her lab, and Bob has this sequence of of bits that he has obtained from measuring, sometimes in the 0-1 basis, sometimes in the plus-minus basis, the bits, the qubits that he has received from Alice. Okay, so now, in order to get the key that they are going to use then for the one-time pi protocol, they communicate over a classical channel, which again needs not be secure, okay? And Alice tells Bob which are the bases that she used to encode each of these qubits, okay? Why is this useful? Because now Bob can check whether he measured in the correct basis or not. If he measured in the correct basis, then he would have obtained exactly the same bit that Alice wanted to send to Bob. Okay, so in all those bases, in all those bits or qubits in which Bob measured exactly in the basis in which Alice intended to send the qubit, then Bob has recovered exactly the bit that Alice wanted to send. Okay, this will happen in average half of the time, for half of the bits. So if they want to share a key of, let's say, 2000 bits, then Alice must prepare at least 4000 qubits, and then they will have to discard some of them because they are not sure that Bob has measured exactly what Alice intended to. Okay, here I'm showing you a picture with the whole protocol. We are talking here about the qubits and photons. In this case, the qubits are implemented as photons, and the different states are the polarizations of these photons, but it's really not important, although this is what is usually used in practice. Okay, but what is important is that if Alice is using the 0 plus basis, the 0, 1 basis, this is what here is denoted with this horizontal basis, then he is sending the zeros and ones. And if she chooses the what we call the diagonal basis, she's sending plus and minuses, okay? And then here we see what are these are the encodings of Alice. For instance, she encoded this in the diagonal basis, she encoded this in the horizontal basis, and these are the bases that Bob chose to measure the bits, okay? And you see here that in the cases in which the bases coincide, then they obtain exactly the same bit, okay? So they can recover some of these bits, okay? So this is the protocol, the BB8 protocol in a perfect situation in which we have perfect qubits, perfect communication channel, and we have nobody trying to eavesdrop, okay? But of course, this is not what we want to address, because if we have something like this, we don't need to do all this conjugate coding and all these protocols, okay? So what we want to know is whether this is secure, whether we can somehow prevent Eve from accessing this sequence of bits. And here, well, I'm going to show you only one of the possible situations. There are many different attacks that have to be considered, and in the literature, all of them have been studied, and it is possible to show that if Eve respects the laws of physics, the laws of quantum mechanics, then she cannot learn this key that is going to be shared by Alice and Bob. Okay, so this is something more secure, stronger than relying on the assumption that some algebraic problem is difficult to solve. This is relying on the correctness of the description of nature that we have. Okay. And what happens here is that I'm going to describe an attack, which is something that Eve could try to do, and we are going to see that this is impossible, or that this would not succeed because Alice and Bob can notice that something strange is going on, okay? So let's imagine that Eve has access to the quantum channel and that she intercepts the qubits that Alice is sending to Bob, okay? So she gets one of these qubits, and then she tries to learn what this qubit is, what is the state of this qubit, and then resend the same qubit to Bob, okay? This is something that, well, might seem that could work. I intercept, I learn what is Alice sending to Bob, and I send the same, okay? The problem here is that Eve does not know which is the basis in which Alice is sending the qubit or the bit to Bob, okay? So she could observe 0, 1, plus or minus, okay? And in order to know which of these qubits Alice is sending, she can only do two things. She can just move rotate the quantum, the Bloch sphere around, apply a quantum gate, or measure. The problem is that these rotations will always preserve the angles. And in particular, for instance, Alice cannot distinguish between 0 and plus, because in the Bloch sphere, these two states are at right angles. And remember that in the Bloch sphere, this does not mean that they are orthogonal. It means that they have some overlap. In fact, if I try to measure plus, I will obtain 0 with 50% probability, okay? So whatever Eve tries to do is impossible to completely distinguish which of the 4 possibilities Alice is using, okay? So if she tries to do this, she will, for instance, sometimes measure 0, And she might think that Alice is trying to send 0, but maybe Alice was sending plus or minus. And when if resends 0 to Bob, then Alice and Bob can notice, because if Bob measures this in the correct basis, which was the plus minus, when Alice and Bob share some of the bits that they have measured with the same basis to check if everything is correct, they will detect that there is something fishy going on. Okay, they can detect that someone was tampering with the qubits. Okay, another thing that you can try to do is, well, I don't measure if I don't measure the bits yet, the qubits yet, but I keep them and I keep a copy of them and I send the original qubit to Bob, and then I wait until Alice makes the basis public, and then I measure. Okay, and this could work if could perfectly copy the state of a qubit. But this is something that is not possible. Remember that in the first lecture, I told you about the no cloning theorem, and we will explain it in this lecture. We will prove that it is impossible in general for an unknown state to perfectly copy the state in a different independent qubit. So this is something, again, that she cannot do. Okay? And as I mentioned, there are other different attacks that Eve can try, and all of them fail. Okay, so this is a very beautiful way of seeing that this possibility of encoding in different bases that are not distinguishable among themselves, it's very, very useful for this task. This is something that can be done in practice, and in practice you need to address the possibility of having some problems, of having, for instance, errors in the quantum channel or in the devices that are used to measure or to manipulate these qubits. Also, we have to address the possibility of, in fact, being someone trying to tamper with the whole process. And then after all these phases, there is another phase which is called the information reconciliation and privacy amplification. I'm not going to go into the details of this phase because this is purely classical. It has to do with, for instance, classical error correcting codes and randomness structures. There is a lot of information about this in one of the courses that I have recommended in the list uploaded to the Indico page, the one that is called quantum cryptography, and you can check them there. But this is something that you can address and you can do, okay? And in fact, in practice, this is something that has been done, and it's being done more and more. In fact, more than 10 years ago, I think it was in 2009, CERN participated in one of the first quantum key distribution networks in the world. In fact, I think it was the first international quantum key distribution network, because you can see here that one of the nodes, the one at CERN, in fact, it was situated very, very close to where I'm sitting now. This red line is the French border. This is Switzerland. This is France. So part of the network was technically in France. Okay, and then we had also nodes in Geneva. This was in collaboration with the University of Geneva and with a company that is called ID Quantique, which are world leaders in quantum key distribution and quantum random number generation. Okay, so this is something that was done more than 10 years ago. It lasted for more than 1.5 years. You can read details about this prototype on this paper. And now CERN is still working on this kind of quantum key distribution protocols and networks. We are part of what is called the OpenQKD, the Open Quantum Key Distribution Network. And we are working with different companies and universities and research institutes in order to stand these networks and make them more useful. Okay. Well, I had prepared some other variations over different protocols that you can do with 1 qubit, but maybe they are not so interesting. Just let me mention that you can do cryptography, not key distribution, but real cryptography in which you encrypt data quantumly. For instance, with this CAC protocol, which uses rotations, you can do something that is called the quantum one-time pad, which is similar to the one-time pad that we saw for the classical case. But here we need 2 bits. This is a very beautiful protocol that can be used, for instance, in what is called blind quantum computing, in which you can send your encrypted qubits to a quantum computer that you do not trust, and ask this quantum computer to perform some operations on these encrypted qubits, and then you recover the information, the result that the quantum computer sends you, and then you can de-encrypt this data to obtain the correct results without the other party learning anything about what the data you are using. Okay, this is also very interesting. There are many different protocols, and some of them are based on this quantum one-time pad. And there are other protocols which use just one independent qubit, just 1 qubit. For instance, other quantum key distribution protocols, the B92, the SARC-04, which was also used in this network that I was telling you about, the 6-state protocol. There is also this very interesting idea of quantum money that was proposed by Wisner, and in fact, this was the first proposal of the use of this conjugate coding. It was not very well received at the moment, and then Bennett and Brassard heard about this possibility of conjugate coding and developed this quantum key distribution protocol. You also have this Elitzur-Weidman bomb tester, which is also very interesting. You have information about this, for instance, in the lectures that I have included in the list of recommendations by Ryan O'Donnell. Protocols for quantum position verification, even machine learning with just 1 qubit. This is a very recent work by the team of José Ignacio Latorre at Barcelona. I will probably tell you something about this when we talk about quantum machine learning. Okay, so there are many things that you can do with 1 qubit. Of course, this does not exhaust what we can do with quantum computing. This is just the beginning, but this is quite an impressive number of things that you can do just by exploiting this superposition and this impossibility of distinguishing states from others if they are not orthogonal. Okay. There is one question here that I have received. I will ask you now also to pose any question that you may have about what we have explained so far, because I'm going to give you a demonstration of this protocol with Qiski. Okay, so the question is, as we use Hilbert space for qubit representation, what about quaternion space? It helps better to make multiple transformations. And for the example of circuit with simulation using gates, could you give an example of simple calculation like A plus B? Okay, well, the first part of the question. Can we use like quaternions or other structures to represent qubits? Yes, what we are going to do after I show you this demonstration of the BB884 protocol is to see what we can do with 2 qubits, and then we will have 4 numbers there. Okay, so in a sense, yes, we can of course expand the Hilbert space. That is, in fact, much of the appeal of quantum computing, to have a big Hilbert space. Okay, about the calculation A plus B. Okay, you can do these simple calculations I mean, these arithmetic calculations with a quantum computer. I will talk more about this later when we talk about multiple qubits in a system. But this is something that in general, it's not very interesting. I mean, what you are interested in doing with a quantum computer are operations that cannot be done efficiently in a classical computer, okay? There are situations in which, of course, you need to do these arithmetical operations, for instance, in Shor's algorithm for factoring, okay? But this is something that in general, we know how to do very easily. I mean, you can take any arithmetical operation and transform it in an efficient operation in a quantum computer. There is a simple way to do this. And this is something that is not, in general, so interesting. Of course, you want to optimize this, for instance, for Shor's algorithm, but what we want to explore is the purely quantum things that you want to do with a quantum computer. Anyway, I can try to do an example of this kind of situation. And in fact, when we will study next week Deutsch algorithm, I will refer to this kind of thing. Okay. I don't know if there are other questions. Yes, somebody is asking me, did I understand correctly that Bob has received only half of the information? Yes, in general, in average, he will receive half of the key, but this is a random key. What Alice and Bob want is a sequence, a random sequence of bits that they then can use for the one-time path. So what they need is a key which is random, okay? So they don't care which bits of this initial sequence that Alice generates go then into the key. They just want a key that is random, and they want to have exactly the same key, okay? So what is important is to generate an initial sequence of bits which is long enough to account for the possible bits that they do not measure in the same basis, and for the different bits that they have to use in order to detect if someone is listening to the channel, or if they want to, or the bits they need to do information reconciliation and privacy amplification. So they can, if they need 1,000 qubits, maybe they generate 1,000 bits, maybe they generate initially 2,000 or 3,000 or 5,000, and then they will retain some of these bits in their final key. Okay. I don't know if there is any other question. Okay, so then I will show you an implementation of, very simple implementation of the BB84 protocol. Oh no, this is not what I wanted to. Can you confirm that you are seeing my browser with the IBM Quantum Experience?
Yes.
Okay, thank you. Okay, so we are going to use the notebook that I have uploaded to the Indico page to illustrate how this BB84 protocol works, and to show you some new things that you can do with circuits in Qiskit. I want to, with these notebooks at the same time, illustrate the protocols and algorithms that we study, and introduce new concepts or new things that you can do with Qiskit. Okay, so let's hope that this works. If not, I have a plan B and a plan C this time, so don't worry. Okay, so, well, it seems again that this is quite slow. Let me wait a minute. I have already uploaded my notebooks ahead of time. If you want to do it now, you can click here, import, and then you select the notebook from your computer. You download it first from the Indico page, and then you import it here. Okay, so let's see. Okay, this time it worked. And we have here the code for this BB8E4 protocol. So what I do first is to create just a circuit for random generation of bits. Okay, remember that we need this in several different moments of the protocol. When Alice generates the initial sequence of bits, when she decides which is the basis in which she wants to code each of the bits that she's going to send to, yes, I can make it bigger. Okay, is it better now? I can probably do it even a little bit, not much bigger because I have here the chat and the list of participants and then I don't see it myself, but I guess this is better. Okay, thank you. Here I'm preparing this circuit that we already know how it works to generate random bits. Okay, we need it for the initial sequence of Alice and for the decisions of Bob and Alice to code and measure these qubits in different bases. Okay, so I'm going to use it to generate, in this case, 100 bits. Okay, if you run it, you will obtain different ones because this is, of course, random. But Alice, in this case, would have this sequence of bits. Now, well, something that it's interesting here is that I'm using this flag here that we didn't use last time, which is memory. Okay, so in the previous notebook, we only wanted to see how many zeros and how many ones we obtain when we measure the qubit. Okay, we wanted to see if the proportion was more or less 50%. But here we need the bits themselves. So if I set this flag to true, I can then, with get memory, recover the whole sequence of measurements. Okay, so this is something that you want to do if you want to access the concrete values that you obtain when you measure the circuit. Okay, so these are the bits for the initial sequence from which we are going to extract the key, and these are the bits to decide in which basis Alice is going to code each of the qubits. Okay, Bob also can do this generation of random bits ahead of time to select which are the basis in which he's going to measure, but this is going to be independent from Alice. Okay, in this case we are doing this all in the same notebook, but this should be done independently. And now here what I do is to simulate with a circuit. Of course, this is not going to happen in an actual quantum computer. It's going to happen in Alice's device on the quantum channel and then on Bob's device. Okay, but here I'm simulating it as if the qubit travels from one way to another through the quantum channel. Okay, so the first part is to code the bits, the qubits that Alice wants to send. So if she wants to send a 1, she needs to apply the X gate. Okay, and then if she wants to code in the plus minus basis, she needs to apply the H gate. Okay, and then when Bob, here is where I suppose that this Bob is sent to this qubit is sent to Bob, and then Bob receives, and if he decides to measure in the minus plus basis, then he has to apply the H gate, and then he measures. Okay, so let's see what happened. Well, what happens is that then Bob obtains a sequence of zeros and ones. Okay, each time that he measures, he obtains a 0 or a 1. Now they communicate over the classical channel, and Alice tells Bob which are the bases in which they coincided, okay, or which are the bases in which she coded the qubits, and then Bob can say, well, I used the same basis, or I used a different basis. Let's keep these bits in which we both use the same basis. And in this case, as you can see, they agreed, or they coincided in exactly 51 positions, and they will share this key of 51 qubits. Okay, so this is the protocol. I have a question here. We represent a qubit for electron in static movement, only considering its spin rotation. What about its movement? How to know its trajectory and its qubit position is affected by its movement in space? Okay, so, well, this is more about how to implement the qubits. I told you in the first lecture that there are different ways. For instance, these quantum computers that we are using on the IBM Quantum Experience are based on superconducting technology. They are not based on spins, okay? There are other proposals to use spins as qubits. And I'm not an expert in this kind of technology. I'm no physicist, I'm a mathematician and a computer scientist. So I assume that, well, these qubits behave as they have to behave. And the information that we need about the qubits is not the position or the trajectory or something like that, only the information related to, for instance, whether the circuit is circulating in one direction. This will be, for instance, the 0 state, or the other direction, this would be the minus state. Or if we have a photon, whether the polarization is horizontal or vertical or diagonal. This is related to the information about the two state that we want to work with, the qubit that we want to work with. You can find more information about this in many different places, but I'm not an expert in the physics of the implementation of qubits, okay? Okay, any other question? No? Okay. So let me go back to the here, sorry, to the slides. And then, well, I have told you about one qubit systems, things that are very interesting that you can do with one qubit systems. But of course, this is not all that you can do with quantum information processing or with quantum computers. Now we are going to study what happens when we have two qubits in our system, related to some of the questions I have received today, okay? And you will see that in this case, we will be able to exploit a different property of quantum systems, which is called entanglement, that is going to allow us to do also very, very interesting things, okay? In the first part of today's lecture, we saw how superposition and this impossibility of distinguishing different states, which in the end has to do with the uncertainty principle, because for the physicist attending the course, the problem here is that you are measuring, or you try to measure at the same time, observables which do not commute, okay? So this is related to the uncertainty principle, allows us to do some very, very interesting things, okay? But when we move to two qubit quantum systems, we can also exploit this entanglement property, which is very, very interesting, okay? So what happens when we have two qubits? When we have two qubits, of course, we know that each of these qubits can be in the state 0 or in the state 1. And then for the two qubits, we have 4 different possibilities, which we represent with these sketch and this symbol, which is called a tensor product. Okay, this is the tensor product of the states of the two qubits. Normally, we are going to omit this, and we are going to just write one ket next to each other, or even both states inside the same ket, okay? But we are always meaning this. I will talk more about tensor products in a minute, but for now, it's very easy to see that, well, if we have two states, they can be both of them in 0 or 1, they can be in 0, 0, 0, 1, 1, 0, 1, 1, okay? And of course, the whole system is going, it can be in general in a superposition now of the 4 different possibilities, okay? So the general expression for a 2-qubit system, for the state of a 2-qubit system, is a combination of the 4 possible basis states of 0, 0, 0, 1, 1, 0, 1, 1, with these amplitudes, alpha 0, 0, alpha 0, 1, and so on, which are again complex numbers, and again, their absolute value square must add up to 1. Why is it so? Well, you can imagine that this is related to the probabilities that we obtain if we measure each of these, one of these states, and we obtain some result. So when we measure a general 2-qubit system, a 2-qubit state, we can obtain either 0, 0, 0, 1, 1, 0, or 1, 1, with a probability that is exactly the absolute value squared of the amplitude that goes with exactly that state in the superposition, in the linear combination that forms the 2-qubit system. Okay, so that is why we need this to add up to 1. This is exactly the same situation we had with a 1-qubit system, but now we have 4 possibilities, okay? But we also have a different choice or a different possibility to measure a 2-qubit system. We can measure both qubits at the same time, but we can decide to measure just one of them, okay? What happens in this situation? What happens in this situation is that if we measure, for instance, the first qubit, then it is going to collapse to either 0 or 1, okay? If we measure the 2 qubits, both collapse to 0, 0, 0, 1, or whatever, okay? But if we measure just one, it will collapse to either 0 or to 1 with a probability that is given by the coefficients that go with the states that have exactly the value that we have measured in the first part. So for instance, if we measure the first qubit and we obtain 0, the probabilities come from this state and this state. These 2 states in which the first qubit is 1 do not intervene because this is not what we are obtaining, okay? So in this case, what we obtain is 0 with probability that is the sum of the squares of these 2 amplitudes of the absolute value of these 2 amplitudes, okay? So the probability of this result and the probability of this result added, okay? And then the new state that we obtain is this one here, which may seem very complicated, but notice that we have here is that we have a superposition in which we have the 2 states that are compatible with the result that we have obtained. We have obtained 0 in the first qubit, okay? So we can have either 0, 0 or 0, 1. We are uncertain yet about the result or the state of the second qubit, okay? And of course, these go with their corresponding amplitude, and we need to normalize. We need to divide by this value in order for these amplitudes to respect the condition of when squared adding up to 1, okay? For the case in which we measure 1 on the first qubit, it is similar, but now we would have the states which are compatible with the first qubit being 1, okay? And if we measure the second qubit, it's again similar, okay? So in this case, we can measure both qubits, or we can measure one, and the state will collapse completely or just partially, depending on whether we measure the whole state or just part of the state. Okay, so this is about the representation of qubits as a superposition, 2 qubits as a superposition, and how to measure it. Again, we can think of these systems of 2 qubits as vectors, and we can represent the different amplitudes of the state as a column vector. In this case, we will have, of course, 4 components in this vector. And again, we can compute the inner product of one system of 2 qubits with another system of 2 qubits by using row and column vectors, or we can use, and in this case, it's going to be many times more convenient, we can use again Dirac notation by noting that basis states that are equal have inner product which is 1, and basis states that are different are orthogonal and have inner product which is 0. Okay, and since we have a column vector that has 4 components, the gates that we can perform on these 2 qubit systems are given by matrices of size 4 by 4. Okay, in this case, unitary matrices, but now we need 4 rows and 4 columns. Okay, how can we obtain these matrices, these quantum gates? The simplest case is to have one qubit gate that acts on one of the qubits of the system, another qubit gate that acts on the other qubit of the system. And any of these 2 qubits gates, 1 qubit gates, can be the identity. Okay, so we can also have the case in which we are applying just one gate to one of the qubits, and then we just simply act like the identity on the other. Okay, so we have these matrices, these gates A and B that are acting independently on the 2 qubits, and this is what we call the tensor product of the 2 gates. Well, the formula for the tensor product is this one here in this equality of matrices. It's not very difficult. At first may seem a little daunting, but it's not very difficult to understand. What we do here is just to substitute each of the positions of the initial or the leftmost matrix with a copy of the second matrix times the coefficient that was in that position in the first matrix. Okay, and we obtain this. But it's very easy to understand what is the action of this tensor product. The action of this tensor product is just that the first gate acts on the first qubit, the second gate acts on the second qubit. You can see, or you can check if you want to, that if you do this and then you compute this tensor product, to compute the tensor product of column vectors, is the same idea that you have here. You substitute each position with a copy of the rightmost vector times the element that was in that position in the leftmost vector, and you can do this multiplication times this tensor product here, or first apply this matrix and then apply this matrix and then compute the tensor product, and you will obtain the same. Okay, this is a little bit boring, a little bit tedious, but it's straightforward. Okay, and in the book by Janowski and Manucci, I think you have all these completely explained with all the details. Okay, so this is the first way in which we can act on 2 qubits with a quantum gate on each of the individual qubits. But of course, this is not very interesting, because then the qubits are not interacting one with another. So a very important gate that is a 2 qubit gate and that it's not possible to construct as a tensor product, so it will make these 2 qubits interact. It won't have an action independent on each of them, is what we call the C naught or control naught or controlled X gate, which is given by this amazingly simple matrix that we have here, but it's probably, I like to call it the soul of quantum computing. This is probably one of the most important gates that we are going to study. It will allow us to do very, very interesting things, as I will tell you in a minute. Okay, so what this matrix is, or this quantum gate is doing? Well, if you study this matrix here, you see that it takes 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 1, and 1, 1 to 1, 0. What it is doing, and this is the name, this is the reason for the name control node, is to apply a node to the second qubit, but only if the first qubit is 1. If the first qubit is 0, it does not do anything. It leaves all the states alone, or all the values of the qubits alone. But if the first qubit is 1, then it flips the second qubit. It applies a second node gate on the second qubit. That is why we call this a control node. It's a node, but controlled by the value of the first qubit. And we can represent this in a quantum circuit. The usual way of representing this on a quantum circuit is by this picture here, in which this solid or black dot means that we are controlling this gate, which is the X gate. You have seen this gate already on Quirk, for instance. We are using this control on this qubit. And then you can see that X is never going to change, and Y is going to change to Y XOR X, because if this is 0, then Y remains the same, but if this is 1, then Y changes from 0 to 1 and from 1 to 0. Okay, so this is the action. This is the way in which we can represent this very, very important gate. I cannot stress enough the importance of this gate, which we call the CNOT gate, on 2-qubit systems and in other systems with more qubits. Okay, and this is very important for several different reasons. The first reason is that it allows us to create entanglement, and I will talk more about this soon. The second important reason is that this gate allows us to copy classical information. Okay, and this is important, only classical information. I have mentioned the no cloning theorem several different times, and we are going to prove it in just a few slides. But notice that for classical information, it does a copy. It copies the information from the first qubit into the second one, provided that the second one is 0. Okay, and this is also a very important gate because it allows us to construct other control gates and other 2-qubit gates in general. Okay, any question up to this point? Okay, so this is a very important gate, and this is a gate that in general is also sometimes difficult to implement in actual quantum computers. It's more difficult than acting on individual qubits, okay, because you need to make 2 different qubits interact. But in general, you also don't want the qubits to interact too much, because then this can introduce decoherence or noise or different errors. Okay, so this is in general difficult to implement. So in many quantum computing architectures, for instance, in superconducting qubits, in the ones that we are using in the IBM quantum experience, it is not possible to apply this CNOT gate directly to any pair of qubits in the system. Imagine that we have 5 qubits, for instance. We are going to work with quantum computers with 5 qubits. Maybe we cannot apply directly the CNOT gate to qubits 1 and 4, for instance. Okay, we can only, for instance, interact in a given topology with a given set of connections, and that is the graph or the information of the CNOT gates that we can use. Okay, what can we do in that case? Maybe we need to perform or to apply a CNOT gate to qubits that are not directly connected in this topology. Well, in that case, we can use several different things. For instance, we can change the control and the target in the gate by using this circuit here. We use a C0, which is which before and after has these Hadamard gates, and then this is equivalent to a C0 gate with the control and target in the opposite direction. You can check this by computing the matrices, for instance, for this circuit, and checking that is equivalent to the corresponding C0 matrix. Or you can try this on the quirk simulator and check that it works as expected. For that, you only need to check on the basis states, because this is a linear transformation, and if you know the action on the basis states, then you know the action on any other state by linearity. Okay, so this is an exercise for you to check in the way that you prefer that this is equivalent to a C0 gate with the target and control flipped. Also, in order to move the states of qubits to neighboring qubits that can be then entangled or whatever with C0 gates, what we can do is swap states. Okay, so imagine that we do not have a C0 gate. We cannot implement a C0 gate between qubit 1 and qubit 4, but we can implement a C0 gate between 1 and 3 and a C0 gate between 3 and 4. Then we can swap 1 and 3, perform the operation on 3 and 4, and then swap again the 1 and the 3. Okay, and to swap states, we can use this circuit here. Again, this is an exercise for you to check that this is equivalent to swapping the values of these qubits. And again, you can do it with the matrices, or you can just check the action of this circuit on 0, 0, 0, 1, 1, 0, 1, 1, and check that it works as expected. Okay, so this is something that you can do even if you don't have C0 gates between all the pairs of qubits in your computer. Okay, I mentioned also that you can use the C0 gate to construct other control gates. I will not enter into the details here. If you want to, you can check this derivation. This is also explained in the book by Nielsen and Chuang. And this derivation relies on the composition that follows from what we observed about rotations in the Bloch sphere. We could obtain a general 1 qubit gate by a rotation on the Z axis, then a rotation on Y, and then again a rotation on Z. From that, you can decompose the gate also in this way, and then you can use this circuit to implement any control gate that you want. Okay. What it's more interesting to explain is why we cannot copy quantum information, the no-cloning theorem, and how this leads to the property of entanglement. Okay, so finally we are now in the position to prove that it is impossible to copy an unknown quantum state into another one which is independent. Okay, so to prove that, imagine that we have a gate U that when given some quantum state, 1 qubit state, but this works in general for bigger states also, but the proof is similar. But imagine that this is 1 qubit and we want to copy it exactly over this second qubit here that is in state 0. So what we want after the action of this 2 qubit gate is to obtain 2 qubits, each of them in a state psi. Okay, then in particular we need this to act on 0, 0, giving 0, 0, and to act on 1, 0, giving 1, 1. Okay, in this case psi is 0, in this case psi is 1. Okay, this is a quantum gate, so this is a linear transformation. by linearity, if I consider this state here, this will act independently on each of the parts, and then we obtain the linear combination of the actions, okay? But we have said that this is 0, 0, and we have said that this U acting on 1, 0 must give us 1, 1, okay? So this should be the result of any gate that acts like this on 0, 0 and 1, 0. But notice that I have chosen this state here with some clever intent. Notice that this can be written also as this tensor product. I can factor this 0 of the second qubit and write this state here like this. But then I can take psi to be this. And U over this expression here must give me psi tensor product psi. So I should have, after applying U to this expression, which is the same one as this one, I should have 0 plus 1 over square root of 2, 0 plus 1 over square root of 2. But we had obtained a different expression for the action of the gate on this initial state. This expression here is not the same as this one. Why is it not the same? Because here, for instance, if you measure, you have a probability of 1 over 4 of 0.25 of measuring, for instance, 1, 0, or of measuring 0, 1. But if you measure this state, you will never obtain 0, 1 or 1, 0. You will ever obtain either 0, 0 with 50% probability or 1, 1 with 50% probability. So it is impossible. There is no gate, there is no linear transformation that can do this copy here, which you can see is the copy of classical information, and then copy also bits in superposition or qubits in superposition. Okay, so that is the reason why we cannot clone one of these states. This is the reason why, for instance, the attack by Eve, relying on trying to copy the state and then measuring after learning the basis used by Alice, cannot succeed. Okay. This is also very interesting and very important because this kind of state that we have here is what we call an entangled state. Okay, I have mentioned that here you will always measure 0, 0 or 1, 1. Okay, so this is there is a correlation between what you obtain in the first qubit and what you obtain when you measure the second qubit. So let's give this a name. We say that a 2-qubit system, or in general, a state of many qubits, is a product state if we can express it as the tensor product of states with less qubits. Okay, each one at least with 1 qubit. In this case, since we are dealing with 2 qubits states, each one of these should be 1 qubit. Okay, so this is a product state. And the idea of having a product state is that each qubit is behaving more or less independently of the other, and we can describe the state of each qubit with just the amplitudes for that qubit. Okay. However, we can have states which are not a product, Here, I'm showing you 4, which are very important. They are called the Bell states. John Bell was a physicist who worked here at CERN and is one of the fathers of quantum information. I will tell you more about his work probably next week. I was trying to do it today, but probably we won't have time. And he worked with disentangled states. He studied disentangled states in part as a response to a famous paper by Einstein, Podolsky, and Rosen, which stated what is sometimes called the EPR paradox. Okay, and he studied these states and reached very, very interesting conclusions about entanglement and the relationship of these to the classical or quantum nature of reality. We will explore this further in the lecture next week. Okay, so you can check easily that these states are not product states. They cannot be written as the product of two independent qubits. Because if you try to write them as product of two independent qubits, you will obtain amplitudes that are not zero for the basis states 0, 1, and 1, 0. And here you see that there are no parts of these states that are 0, 1, or 1, 0. Okay, and these are what we call entangled states. Entangled states. And the interesting thing about these entangled states is that they have very strong correlations, even if these parts of the system are separated. As long as they keep this entanglement, they don't interact with other things. If they are entangled and we separate them, when we measure them, we will obtain very, very strong correlations between the results of one measurement and the other. And this is something that we will see next week cannot be explained with classical physics, just with classical physics. It needs quantum physics to be explained. Another interesting property of these 1 qubit, 2 qubit systems or entangled systems of many qubits in general is that when you try to describe the state of the parts of the qubit, of the parts of the two qubit system, you cannot describe the whole system just by combining the description of each of the parts. Okay, so you need a global description of the system. If you know everything about one of the parts, everything about the other part, that is not enough to reconstruct the whole state of the system. Okay, to study this, we would need to introduce what are called density matrices. Of course, the physicists attending the course know perfectly well what density matrices are. For the rest, you can check, for instance, the book by Siegelman that I have included in the references. But this is something that I'm not going to work with in general in any of the lectures. If you want to explore that, it's also a very fascinating topic. But I won't have time to cover that. But it's interesting to understand that when you have entangled states, then you cannot describe anymore the whole state as a combination of the descriptions of each of the parts. Okay? And to explore these correlations and these interesting properties, we are going to implement and run probably what is the next simplest circuit that we can run in quantum computation, after the one with the Hadamard gate and the measurement that we studied last week. But this is also a very, very interesting circuit and very, very useful. You will see that this is part of many of the protocols that we will study further on the course, because it's able to create these entangled, these Bell states. Okay, so here we have a Hadamard gate and then the CNOT gate. And what we are going to do is to see what happens when we measure first the top qubit and then the bottom qubit. Okay, so initially, of course, the state is in the system is in the state 0, 0, which is a product state. Each qubit is happily living in his 0 state with no relation to the other. And then we apply the H gate, and you can check that this transforms to this state, which is, again, you can check, a product state. Okay, so now we apply the CNOT gate, and you can check easily. This is also an exercise for you, very easy, that then we create one of these Bell states that we have been mentioning. Okay, then what happens if we measure the first qubit? Well, if we measure the first qubit, we can obtain 0 or we can obtain 1 with 50% probability. Okay, but then imagine that this collapses to that the state of the result that we obtain when measuring the first qubit is 0. Then the whole state collapses to 0, 0. And when we measure the second qubit, we won't obtain 1. We will obtain always 0. Okay? If we measure 1 on the first qubit, then the state will collapse to 1, 1. And when we measure the second qubit, we will always obtain 1. And what is also interesting is that if we measure in the other order, if we measure the second qubit, we can obtain 0 or 1, but then when we measure the first qubit, we will obtain the same value that we obtained for the second qubit. Okay, so this is a correlation that, together with other correlations that we obtain with this kind of states when we perform some transformations and then measurements, cannot be explained by classical physics. And we will talk more about this next week. Okay, is there any question about this? Okay, so now let me show you how to check this interesting property of entanglement with the IBM quantum experience and with Qiskit. Okay, so now you should be seeing my browser again with the IBM quantum experience. Yes, and I have uploaded here this notebook for the entanglement circuit. Okay, I'm going to open it, and I'm going to show you what I'm doing here. Now I'm working with 2 qubits. Okay, so this is the first circuit that we create with 2 qubits. We have here to specify that we need 2 qubits and 2 bits, 2 classical bits for the measurement. And here we apply, well, the circuit was just a Hadamard gate and then a CNOT gate. We apply the H gate on the first qubit, and then we apply a controlled X, a CNOT gate, which has control 0 and target 1. Okay, and then we measure both qubits on the classical bits. Okay, so let's see if this works. Maybe it's a little bit slow. Okay, it works. Okay, so now I'm going to run this on the quantum simulator, and you see that out of the 4 possible values that you can obtain when you measure a 2-qubit system, we only obtain 0, 0, and 1, 1. Okay, this is because this is an entangled state with part 0, 0, part 1, 1. Also, we can access the amplitudes and the probabilities of this state that we have created. Okay, so what I'm going to do is create a circuit that has no measurements now, run it on the state vector simulator, and then with these orders here, we can obtain from the state, we can obtain the amplitudes of the different basis states, and then of course also the probabilities. Okay, so I run this, and you see that the amplitude of 0, 0, and 1, 1 is of course 1 over the square root of 2. And the probabilities are, well, up to the precision here, 0.5%, 0.5. Okay, now I'm going to try to run this on the IBM quantum computer. And this is probably going to be a little bit more difficult. Oh no, okay, it's working today. Perfect. Okay, so what I'm going to show you is that, well, up to now we were running circuits of just 1 qubit, and we were using this computer which is called Armonk. But now we are going to use more than 1 qubit. Okay, so we want to select among all these different devices that I have here. Probably some of these are not available to you. I don't know, because I have access to some research devices. But anyway, you will have some of these with 5 qubits, with 15 qubits. Okay, and then you have several different informations. I don't have time now to explain this, But depending on this information, for instance, the number of jobs that they have, you want to choose one over the other, okay? Also, you can obtain more information, and probably I will discuss this first time next week, because this is very important or very interesting information about the devices here, about the connectivity, about the errors, okay? You can try to read it on your own, but now I want to show you how to select the least busy device, okay? Now we have different devices, all of them with 2 or more qubits. So I'm going to filter among all the devices, those that have at least 2 qubits, that are active and that are not simulators, okay? And with this order here, with this command, I can select the backend that is the least busy, okay? So the one that has less pending jobs, okay? And well, this may take some time. Probably some of you are running this. Well, in this case, it has selected IBM Q Athens. And you see that here in the queue, we have 12 jobs. So probably it won't finish before it's time to close this session. But you can try to run this on your own, and then if you run the last cell on the notebook, you will compare the results on the device, on the actual device in which you are running, with the results on the simulator, okay? And you will see that in addition to 2 big probabilities for 0, 0 and 1, 1, you will also have some small probability for 0, 1 and 1, 0, okay? In a perfect computer, in the simulator, on paper, this should not work. This should not happen, okay? But as I've mentioned, the implementations are not perfect. The CNOT gates are sometimes difficult to implement. Also, the measurements are sometimes not correct or can introduce errors, okay? So this is the reason why you will observe some small probabilities for also 0, 1 and 1, 0, okay? So I think that is all for today. Thank you very much for the attention. I don't know if the people in the Zoom meeting have any question. I will try, if there is a problem with the slides, I will try to solve it now, so you can download the new ones for this session. Thank you very much again. You will be able to access the recording probably on Monday. And again, I'm